Okay. Hello, everyone. Today's seminar will be about basic cryptographic mistake. So I know that not everybody has a cryptographic background, so I will try to give you some basic definitions and then give some examples of why people make some basic mistakes when they implement cryptographic algorithms. So let's start with a few definitions and what kind of things are solved by cryptography. So some of the security problems solved by the cryptography are as follows. We can provide the privacy of the data. So by encryption, we actually provide privacy, but the data might be in different stages. For instance, we can provide the privacy of data at rest. For instance, your files that in your hard drive, they are the data at rest, but we also provide privacy during communication. So we also provide privacy for data in transit. But in the last years, we also obtained privacy for data in progress. This means that we can now work on encrypted data. In previous years, in order to change something in the encrypted data, we have to decrypt it back, make a few changes, and then encrypt it back. But now we can make those changes while keeping the data encrypted. So this is achieved by full homomorphic encryption, and it is actually a good thing to have in cloud security. So you don't need to trust the cloud provider anymore. You can keep your files encrypted at all times and make modifications while they're still being encrypted. But of course, this requires some, these full homomorphic algorithms are not very efficient right now, but in the future, we believe that they will be more efficient. We also solve the problem of integrity of data. These are done by cryptographic hash functions. We also solve the problem of user and data authentication. And by digital signatures, we solve the problem of transaction non-repudiation. So let's look at the security and data in transit. So this is actually what happens. Most of the time, two people or actually two devices try to communicate. And whatever the communication channel they use, we believe that it is unsecure. So this could be a wired communication like an Ethernet cable, but this could be also a wireless communication like a GSM communication or Wi-Fi communication. And it is even easier to listen to the communication when it is wireless, because with an antenna, you can gather any data that is transmitted around you. So we always assume that there is an attacker, Eve. So she can listen to this communication channel, and she has also power that she can modify by changing some bits, but she can also add more bits or remove some of the bits. So she can delete or add more bits or modify the current transmission. So we want to provide security even under these conditions, and actually this is what is done by cryptography. So we always assume that whatever you transmitted in all of your life are stored by somebody else, and actually Snowden documents say that secret agencies can actually store 1 month of whole internet communication. So they listen to, and mass surveillance allows them to store everything and listen to all of the communications. They can store all of this data for more than a month, and the metadata of these communications can be stored more than a year. So we always assume that somebody captures our data, but so we try to communicate in an encrypted way so that we don't care if they are listening or not, because since it is an encrypted, the data is in an encrypted stage, nobody can understand anything from our communication. So even if this cryptography is really good and it solves a lot of problems, you might ask that why we hear data breaches and hackings and so on. So let me try to explain how it works. The main problem is as follows. Cryptographic algorithms are at the bottom step of security. So think about it as a pyramid, and at the bottom you have cryptographic algorithms. So If these algorithms are broken or if they're not secure, then the whole security is lost. So it doesn't matter what kind of protocol you are using. If the cryptographic algorithms are bad or broken, then you don't have any security. But we have good cryptographic algorithms. So the security breaches should not occur at this level. So we expect that when people use good cryptographic algorithms, the system should be secure. So even if this is the case, so what happens as follows. A hacker generally does not try to break cryptographic algorithms, but they try to find a way around them. So most of the hackings are done not on the cryptographic algorithms, but they found a different weakness in the system. But if there is a problem in the cryptographic algorithms, then the whole security is lost. And sometimes due to some basic mistakes, this is what happens. So let me give some basic mistakes people are doing. So if you use algorithms that are intentionally weakened by secrecy agencies, then your security is lost. So this is one of the biggest basic mistakes. And the next one is use of short cryptographic keys. So cryptographic algorithms are actually not secret. They are publicly available. You can see how the algorithm works. But for encryption, we use a short key, like 16 bytes or something. So that is the only information that we keep secret. But if you use something even shorter, then the security is lost. So I will talk about how long or how short the secret keys should be. Third one is the most used and one of the biggest mistakes people do. Use of cryptographic codes written by others. For instance, using open source libraries for cryptographic algorithms. So this means that the main security that you need, you trust to somebody else. So you trust a person you don't know, but for some reason they put a code in a GitHub, and so you trust them and use it in your implementations. And if there's a backdoor in that implementation, then your security is lost. Another big mistake is the use of cryptographic parameter selection without cryptography knowledge. And a similar mistake is cryptographic algorithm design without cryptanalysis knowledge. So all of these mistakes are done in the past, and in the following slides, I will show a few examples how these mistakes were done and what kind of results there occurred. Most probably not in this order, but I will tell you how you can do basic mistakes if you don't, if you're not careful about these concepts. So let's start with encryption. Most of the time we use block ciphers, and actually during this Zoom communication we are using a block cipher called AES, which is short for Advanced Encryption Standard, and it uses 256-bit secret key. And idea is as follows. Block ciphers operate on B-bit blocks of data. So this communication, I said that it uses AES. So all my video and my voice actually divided into 128-bit blocks, and they're encrypted and sent it to you. And when they're encrypted, the result is also B-bit blocks. They are combined somehow, and the output is transmitted to you, and you also decrypt it back and see my image, the slides, and my voice. So each block is encrypted by a k-bit secret key. In this communication, Zoom uses 256-bit secret key. And as it is stated here, nowadays we use block sizes this many bits, and the key size for personal use, it should be at least 128 bits. And for military grade security, you need at least 256 bits secret keys. So anything shorter than this, I say that it is easy to break, and I will give a few numbers in the following slides. So let's start why this is, what kind of shorter keys that are used in practice and why this is good. So let me give you the first block cipher example. Probably you heard this name before. It is a block cipher called DES, which is short for Data Encryption Standard. It is a very old cipher designed in 1970s, and it was it became a USA standard, and then the whole world started using it. But the problem is that initially IBM used block ciphers with 128-bit secret keys. But NSA modified this and reduced the key length to 56 bits, which is short even at that time. And it became useless after 1990s because this is a very short key, but people are still using it. I even hear from some Turkish engineers working in important companies saying that 56 bits key is still secure. Nobody will try and brute force attack to break the system, but actually they can, and I will give you an example in the next slide. But there are two problems here. First one is the short key, but the second one is due to its name, some people still think that it is a standard because the name says data encryption standard. And even more importantly, many of the famous web pages or lecture notes still use this when teaching encryption. So until a few years ago, when you Google Microsoft and encryption, you will see a official Microsoft web page where they try to explain how encryption works, and they suggest you how to use data encryption standard. So a lot of people are still using this broken algorithm. So let me give you a more concrete example of a block cipher so that you can visualize what is going on, and I will tell you then why the key length shouldn't be that short. So this is a lightweight IOS standard for block ciphers. So it is a very simple block cipher. It uses a block size of 64 bits. So it actually corresponds to 8 bytes. So any 8 character you write actually turned into 64 bits, and there are 64 lines here in this picture. You choose a key length first. You can either choose 80 or 128. And I will say that 80 is short and you shouldn't be using it. But whatever you choose, from this master secret key, we produce round keys that are 64 bits. So in an encryption, your plain text, which is your input, are written here. They are XORed with your round key, which is a modular 2 addition actually. Then these 4 bits are replaced with 4 bits by looking at this table, which is written in hexadecimal notation. Then the places of the bits are swapped. So this is a single round of the cipher. So you repeat this picture 31 times as written here. And this is how you get an encryption just for one block. So here's 2 mistakes people are doing. The algorithm supports 80-bit key because in some scenarios, maybe you need security for just a few seconds or just a few minutes. So in those scenarios, you can use such a short key. But since this is an IOS standard and it allows you to choose such a key, people are using this key for a longer time to have longer security, but they cannot. You can break this kind of keys maybe in hours if you have huge computational power like a secrecy agency. And another problem is that I look at some of the open source implementations of this block cipher on the internet, and when their implementation has a bug, but maybe it is done intentionally and it might be a backdoor. So even if you choose 80-bit secret key, the implementation actually doesn't care about 16 bits of it, so it actually is reduced to 64-bit key. So again, this is why I always suggest that if you want to use crypto, you have to learn crypto, or you need to get a consultancy from somebody who knows it. Otherwise, you lose the whole security of your system. So let's talk about why short keys are a problem. Let me explain it in this way. So I said that DES has 56-bit secret key. This means that since a bit can be either 0 or 1, you have 2 options. So you have 56 bits, so you can generate 2 to the 56 different secret keys for this algorithm. So this number is actually equals to this many secret keys. So an attacker can capture a ciphertext and a plain text and can try every secret key one by one, and in the worst case scenario, they have to try this many secret keys to find the correct one. So this attack works for every cipher. So key length is important for this reason. So for 56-bit keys, this is the number of secret keys that you can generate. And if you choose 80-bit secret key, this is the number of possible secret keys. But if you move on, as you can see, the number increases exponentially. So for the military grade security, you have such a huge space of secret keys, nobody can try them one by one. Actually, this number is kind of larger than the number of atoms in the observable universe. So it is such a huge number. So you might say that how long does it take if I want to break such a system? A modern GPU can try more than 2 to the 33 keys per second. And in a year, you have around 2 to the 25 seconds. This means that a modern GPU can try 2 to the 58 keys per year. As you can see, this number is larger than this one. So if you want to attack this with a single GPU that you bought for gaming, you can do it in a few months. And if you want to break 80-bit security, you need to have maybe millions of GPUs, so gamers can get together on the internet and work on a few months or years and can break this system too. So short keys should be avoided, but these ones are completely secure with respect to the current technology. So of course, I give the example for a GPU because that is the best thing you can buy, and that doesn't require you to have a knowledge in the system, but you can use dedicated hardware which can exceed this number and perform the attack in a shorter period. But still, current technology doesn't allow to perform brute force attacks to this kind of key lengths. So one of the basic mistakes is that people still think that the short keys are still secure, and this is why they lose their security on the internet. So there are many ISO standards that support 80-bit secret keys. And moreover, some people think that if you use double encryption, we double the security. For instance, since this is not secure, instead of using a single DES, let's perform the encryption operation again, but this time using a different secret key. So they think that since a single DES has 56-bit keys, if we use double DES, the attacker has to try all of these possibilities, which would increase this security to 112 bits. But actually, you can perform a brute force attack to only one part and store them in a table and then attack this one. So this actually, using double encryption, using double DES, increase your security from 56 bits to 57 bits. So this was known for like maybe 20 years. So we thought that nobody would still do this mistake. But recently we observed that some modern cars like Tesla Model S had a problem with their key fob. So people at Belgium at Catholic University of Leuven found an attack so they can clone a key fob of Tesla Model S in 7 minutes. So in order to overcome this attack, the company who provided these key fobs said that maybe we can use the encryption algorithm twice so that the attack now will take millions of years. So they thought that with this firmware update, they can overcome this problem. But 1 year later, same people at Catholic University of Leuven break the same key fob. This time the attack took 14 minutes instead of 7 minutes because of this simple observation. So let me show you another mistake which people do. I told you that the block cipher actually works on B-bit blocks. So our communication now actually works on 128-bit blocks, which I think 16 bytes. So our communication, my video or the slides are divided into 16 bytes of blocks, and they're encrypted with the same secret key to provide ciphertext blocks. And you can concatenate them and obtain the ciphertext this way. So this is the most basic and obvious way to do if you have such an encryption algorithm. But this is the worst thing you can do also, because if some of the blocks here are identical, for instance, if P0 and P2 are the same, Since you are using a deterministic algorithm with the same secret key, then the output will be the same. C0 and C2 will be the same. So you might say that, okay, but this is maybe a low probability, then why should some of the input will be the same? So let me show you an example by encrypting a bitmap file. So this is our university logo. Think about it as a rectangle. As you can see, there are many white pixels here. So they're repeating itself. So when you want to encrypt this image file, you have to divide it into blocks, but most of the blocks will be identical. So this will be the result if you perform encryption using the method I just showed you. Here I'm using AES, Advanced Encryption Standard, which the whole world uses, and which we assume that it is secure, but even using the best encryption algorithm we have, you see this is the result. So if we go back to the image itself, this is the encrypted version. Just by looking at the encrypted version, you can guess what the image is. So the problem to overcome is to make a connection between these blocks, perhaps, like adding this part to this and so on. So even if the P1 and P2 are the same, now C1 and C2 will be different. But this is one way of doing it. What we suggest people to do is as follows. This is actually a counter mode of encryption, and this is what your actual mobile phones are using. So if you enabled encryption, and if you have an iPhone, they come with default encryption. So in the background, when you took a picture with your iPhone, when it writes that image file to your iPhone, they actually encrypted it using this format. So instead of encrypting the image itself, what they do is choose a nonce, which stands for a random number that should be used only once, and you choose a counter. So for the first block of your image, you encrypt this counter, and the result is XORed with your block and obtain the ciphertext block here. Then you increment the counter by 1 and do the same step. Increment it one by one and so on. So as you can see, here we are not using your data initially. So this is the picture you have taken, for instance, with your phone, but we are not interested with that first. We actually encrypt something else as some value that is randomly chosen. And in a mobile phone, actually this number belongs to the block number of your data storage. So it is encrypted. So here you are actually producing what we call a key stream here. Then you simply XOR that key stream with the file or the image you are encrypting, and this is the output. So we always recommend to use this kind of mode of operation, and actually Zoom uses something similar to this during this communication. But instead of the counter mode, they are using Galois counter mode, but the idea is the same. So here I told you that the nonce means that it is a random value that you have to use only once. So for a picture you have taken, for instance, for your phone, you choose some numbers here. I told you that that will be the block number in the data storage. So when you take another picture, since you cannot write it on the same place, you have to write it to a different place on your data storage. These numbers will be different. So your mobile phone always chooses these numbers differently. But what happens if you choose the same nonce for encrypting two different files, right? So we actually said that this is a bad idea maybe 20 years ago. But what happened is that people use this idea again. For instance, like I think 10 years ago, the ransomware became famous because people realized that when a Trojan actually infects your computer, they can do whatever they want. They can delete some of your files or, get control of your computer and so on. But people said that instead of doing that, maybe we should encrypt all of the files in the person's computer and then say that, we encrypted all of your files. If you want to recover them, just give us some Bitcoin so that we can recover all of your files, or otherwise they are all lost. So this is what a ransomware actually works. So, but we observed that the first Turkish ransomware used this counter mode with the same nonce for every encryption. So we observed that. So what happens is as follows. Let's say that you have two files, M1 and M2, but you use the same nonce and counter for encrypting both of them. So what happens is as follows. If you go back to picture, since you use the same nonce and counter here, you produce the same key stream here, which we represent with K here. So the encrypted versions of two files in your computer becomes actually M1 XOR K, which is C1, and the other one becomes M2 XOR the same K, C2. So these Ks actually should be different if you have used different nodes, but they didn't. So this is where the problem lies. So what you can do is as follows. You can just XOR C1 and C2, which would, the Ks will cancel out because this XOR operation is modulo 2 addition, and you end up with M1 XOR M2. From here, you might do some techniques to capture M1, M2, but more importantly, what we did as follows. This actually happened to a professor at the chemistry department, and all of his files were encrypted in this way. So we said that since we know some of the original files because there was a PDF file on his desktop, which was actually a paper he published himself. So we went to Elsevier and obtained that M1 file from there. So what we did was follows. We had the C1, which is the encrypted version of the file, but we downloaded the non-encrypted version of it from the internet. So we XORed them. So this way, actually, we obtained K. And by using this K, we XOR it with C2 now. Ks cancel each other. Since XOR operation is just modulo 2 addition, we end up with M2. So this way, we recovered back all of the files. So knowing K means that you can decrypt everything. So a very famous ransomware failed to work initially, which was good for us. We didn't have to pay any Bitcoin to recover our files. But something very strange happened. So this became known by everybody. And non-cryptographers didn't understand where the problem lies. So they said that this counter mode is a bad mode of operation. So I see a lot of Turkish talks where people suggest not to use this counter mode of operation. But again, as I told you, your mobile phone, your iPhone, your Samsung, or our Zoom communication here actually uses this mode of operation. So the mode of operation is secure. What is not secure is to use the same nodes twice, which you should avoid. So this is one of the other basic mistakes people do. Okay, so if you go back to our example, this was the picture, and I told you that this is how you encrypt it in a bad way. But if you use the counter mode, this is what you should see. So as you can see, it is full noise. There are no patterns to tell you what the original image was. And you cannot guess or have any idea what the original image looks like. So let me show it to you again. So you should use this one. Okay, so let me move on to some more examples, and I need to talk about lightweight cryptography. So evolutionary change in computing and information technologies actually worked as follows. Initially, there were many users, but only a single computer. Probably none of us are that old, but we started our life with the personal computer. So one user had one computer. But nowadays, due to the increase of computational devices and with the help of Internet of Things, now we have one user but many computers. We have our mobile phones, tablets, laptops, desktops, our smartwatches, and almost every smart device in our home. So we have a lot of devices that can connect to Internet. But many of these IoT systems run on resource-constrained platforms, for example, mobile tokens without battery, RFIDs or medical implants that do not allow change of batteries. So, if you have a hard battery implemented, you cannot change it all the time. So they have to, conserve battery. And since many IoT devices are extremely cost sensitive, they are deployed because they are deployed in extremely high volumes. This makes them extremely cost sensitive. So in order to make them cheaper, most of the time, the designers do not implement any security in them. So this is the huge problem. But more important, the industry needed for this kind of lightweight cryptography, which would work fast and secure on this kind of smart devices for at least 20 years because of the use of smart cards and so on. They are around for many years. but they became an active research area in academia over the last 10 years. So for this reason, industry deployed several proprietary self-made algorithms and many disasters happened. I will briefly mention 3 disasters. One of them is Keylog, which is used for remote keyless entry. The other one is Mifare Classic Smart Cards. And the third one is A51 Stream Cipher, which is used for GSM communication encryption. So let's start with Keylog. So this is a hardware-based block cipher. It is used for remote keyless entries. So you can open your car doors with just pressing a button, or your garage doors, or even your building doors, and so on. And it was used by many companies. As you can see, many car companies use this algorithm. But academicians found a lot of weaknesses in this algorithm, and I tried to summarize some of the best-known attacks. So in this scenario, the manufacturer also have a secret key which they use in all of their cars, and your remote key fob has a secret key which is designed for you. So if you don't know the manufacturer's secret key and the remote controller's secret key, you can do the following attack. This side channel attack requires 10 traces to obtain the manufacturer's secret key and the remote controller. So this sentence means actually as follows. Side channel attack means here we need a physical access to the key ring. So you have to capture the key fob, press the button 10 times and do some measurements during this process, and then you capture the manufacturer key and the remote controller key. But since every manufacturer uses the same key in all of their cars, getting the manufacturer secret key once is enough for you, because at this point, if you know the manufacturer key, when somebody tries to open the car doors of their cars, you can listen to this communication twice. So you don't need a physical access, just stay close to somebody who is opening their car doors. Then this way you get the secret key. So you can clone their key fob and steal their cars. So this is actually happened in the past a lot. So if you have a very old car, you should be careful about using your remote access button when some suspicious people are around. More importantly, there is a different attack here I like. It is denial of service attack. So while walking around, you can actually reset the internal counter of these algorithms, like the car doors or garage doors. So when the legitimate user tries to open them with the button, it wouldn't work because the synchronization is lost. So if this is happening to you with your garage or building door, this is actually means that somebody is performing an attack. So I mentioned that this is a very old algorithm and happened in the past, but we still see examples in modern versions. So this you can read the whole story from here. Actually, a few months ago, the same people performed better attacks, and they have a video on the YouTube that you can watch. And there's even now books about car hacking. Let me move on to A51. So this uses a short key, like 64-bit key, and this is used in 2G communication, by the way. What you can do is as follows. You can perform a brute force attack for this 64-bit key, but you can store some information from this attack. So 4 terabyte hard drives are sold on the market, so you can buy them and store them in a table, which we call rainbow tables. This means that if you have such a hard disk and an antenna, you can put it in your backpack, walk around and listen to every GSM communication that is happening around you in real time. And SMS has also that similar weakness, so you can read the SMSs of people around you. But again, this was a 2G standard, so if you're using 3G or 4G, you shouldn't be using them, but in reality, actually, it is not. So this is a table taken from Security Research Labs from 2017. You can visit the webpage and look at the current version. I just had this picture because, as you can see in the past, this data is not gathered from whole country. This is gathered from some volunteers, and in those volunteers, they observed that this many percentage used A51. So their communication can be listened in real time by anybody. So this ratios does not change much since, but we moved on to 3G in 2009. But even at 2017, you know, this is what happens. We are using a algorithm that can be listened by everybody. So when you call your mom, you know, you can say, "Hi, mom," but next time you can say that, "Hi, mom," and everybody else who are listening, because most probably somebody else also listens to you. And if the person you are calling has a very old phone, since they wouldn't support the new algorithm, they would be using the previous one, which is broken. So having a modern phone also increases your security. Okay. My third example for this is this Mifare Classic Smartcard chips. This is, I think, the most produced and sold smart card in the world. They use their own cryptographic algorithm. Again, they didn't consult cryptographers, so this is where the problem lies. It is used in public transportation. It was used in London Metro. The Oyster cards were like this, but since it is broken, they moved on to better smart cards, but they are still used in car parking and so on. So if you're living in Istanbul, probably you already have a car parking smart card in your wallet, which actually uses these chips. So you can actually, if you have an Android phone, you can install an application, and you know, if you have NFC capability with your mobile phone, you can just put your smart card at the back of your smartphone, and you can see what kind of smart card it is. So if this seminar were in a physical place, I would you know, check which one of you have this kind of cards and which ones we can clone. So here you can see that the card has a serial number. So this is not a secret information, but most of the time the card readers only check the serial number. So if you copy the serial number of somebody you know, for instance, instructor at Informatics Institute, then you can, you know, copy that and, you know, open the door of the building whenever you want. So this card actually has some 16 secret keys, and there are many attacks that you can break. An online attack takes 10 minutes. So if you steal or borrow a card from somebody, you work on it in 10 minutes, give it back, and then perform some more calculations in 10 minutes, and this way you can clone the card. In an offline attack, and you are passing somebody, if you have an antenna and gather information from the card in a second, you can go home and our GP implementations can clone the card in a few hours. So this is why you should be careful about your smart cards, which are in your wallet, because somebody maybe standing next to you can be trying to copy it. But the hardened versions of these cards are actually somewhat more secure, so these attacks doesn't work directly. But if you listen to valid authentications, for instance, if you pay your meal at cafeteria, somebody can listen to your this communication and capture the secret key and clone your card. For instance, I can show you a RFID tag in my ring chain. So this is actually, this looks like something that opens the, you know, apartment building or something, but this is actually the exact clone of my university ID card. So most of the time I don't carry my ID card on me, but I use this to, you know, open the doors and so on. So as you can guess, our university uses this Mifare Classic 1K smart card. Okay, so I think this will be my last slides. So I will briefly mention a basic mistake people do. RSA is a public key encryption algorithm. It uses simple number theory, so this is why I actually wanted to go technical and briefly mention how it works. So you choose two big primes, you multiply them and obtain the value n, and you choose e, which generates a small number between 2 and n-1. Then you compute the inverse of this number modulo this. So inverse means that d times e has to equal 1 in this modular arithmetic operation. So you compute d yourself. So now you publicly announce n and e. So these are the numbers when people want to send you an encrypted message, they will use these ones. But d is only known by you, and you can decrypt the message. And actually, encryption is very simple. For instance, somebody wants to send you a very short message, M. What they do is as follows. They take the e power modulo n and obtain something which we call the ciphertext and send it to you. Now you receive C, and only you know the D, so you take the D power of C, which actually means that you are taking the D power of M to the E, which means M to the power E times D. But due to some trick here we have done here, and to number theory, this returns back to M itself, so you decrypt the message. So it is as simple as that. But funny thing is, the choice of E is generally is chosen small so that the algorithm works really fast. For instance, sometimes we choose E equals to 3, or sometimes we choose something larger than 65,000 because it equals to 2 to the 16 plus 1. And when you write it in a binary form, there are many zeros and only a few ones, which makes computations very fast. But I realized that some people having slow implementations because instead of using C programming language, probably they use Python or Java, so it takes a lot of time. Some people, I don't want to give the name of these companies in Turkey, but they say that when they put their Smartcard or something, the calculations take a lot of time and the door opens in like 7 seconds and so on. And they told me that they found a solution by changing this E. They say that now they chose E equals to 1. So that the door opens in a very fast way. But the problem is that, and there are many GitHub implementations on the internet which chooses E equals to 1, but as you can see, I said that E has to be between these values. So let's look at what happens when E equals to 1. When somebody wants to send you a message, they encrypt it by taking the first power of it. But taking the first power of any number is itself. So when they think that they're encrypted the message, they're actually sending you the M as the plain text. So a lot of people on the internet now think that they're having an encrypted communication, but due to this simple mistake, they are communicating as a plain text. And you receive this value, which is M. You also take its first power because D also becomes 1, and you obtain M back, which was never changed initially. So this is one of the basic mistakes people do, and I've seen a lot of GitHub implementations where E is hard-coded as 1. You can also check yourself. So this actually gives a very good idea for hackers. So these two actually are the best way to introduce cryptographic backdoors. You know, there's a web page called Stack Overflow where people ask technical questions, and then most of the time people ask cryptographic questions. If you answer them in a wrong way, this way you can introduce backdoor to those implementations. Or more subtly, you can put wrong crypto implementations at GitHub because people don't bother, and just take it from there and just use your code. And this way you can introduce backdoors to cryptographic implementations. So that will be all for me. Thank you for your attention. If you have any questions, I will be happy to answer.